Hello, Aurora lovers. This is Dale Bone from Dale Bone Imaging, and this is Aurora Hunting 101. This is episode 15. What is the solar cycle? Every 11 years, the sun goes through a cycle of increased activity and then a decrease. This is often mistakenly called the solar cycle. The obvious change is the number of sunspots on the sun's surface. The active areas around the sunspots are the primary source of coronal mass ejections, or CMEs. This can lead to aurora. So let's dig into the sun a little bit deeper. The change in the number of sunspots is a sign that the sun's magnetic field is shifting and ultimately flipping. This reversing of polarity happens approximately every 11 years, plus or minus 3 years. It takes 2 reversals, or 22 years, to return to the original polarities. This full cycle is the Hale cycle, also called the solar cycle. The 11-year cycle of the increase and decrease of sunspots is more properly called the sunspot cycle. However, it is incorrectly called the solar cycle. It's just half of a solar cycle. From the aurora hunting perspective, the polarity of the sun does not affect the aurora. Half the sun is one polarity, the other half is the other polarity. It flips. Half the sun is one polarity, the other half is the other polarity. It does not affect the aurora. So let's take a look at the solar cycle and the impact on the aurora. Let's start with the NOAA Space Weather Enthusiast Dashboard. I use this quite a bit. It has lots of useful information, but it is fairly technical. Let's just scroll all the way down to the bottom past the pictures and graphs and the current aurora conditions to this graph. So even here they're calling the 11-year period a solar cycle, so I don't know. Just noticed that. So possibly because originally no one knew about the magnetism of the sun, so all they were doing was counting the sunspots. So the solar cycle, sunspot number progression. So we are currently in 25. This is, the red line is the forecast, and you can see that the numbers are quite a bit above forecast, which is always promising and makes aurora hunters happy. You can see that the last cycle was a little odd looking. So it looks like we're going to be quite a bit above the last cycle, cycle 24, which was in the 2010s, basically 20 teens. And it was abnormally low. So now there's reports that, we've never had as many sunspots in the last 20 years. That's okay, but that's because last solar cycle was abnormally low, and now we're a little closer to average. I don't think it's worth generating articles about it, but there seems to be a whole bunch of articles about that. So if we look back further, across multiple cycles, you'd see that cycle 24, the last one, was really considerably below average. So it's basically the last one in the last 10 or more. So it was the weakest one in the last 100 years, 120 years. So it's not surprising that the current one is above that. It's not, I don't think it's really news. I don't think there's much to read into that. The forecasters expected it to be similar to the last one. Turns out that maybe it's not quite that low. Now they're forecasting it might end early. Who knows? But you can see from here that, we might have quite a few sunspots right now, say 100, but there's been times when there's 300 or more. And if we drag it all the way back to the entire data set that NOAA's showing, you can see there's quite a bit of variation. There has been times when like cycle 5 is pretty low, but generally this one and this cycle and the last one are low so far, although 25 looks pretty promising and does not look abnormal at all in comparison to some of the other ones. If you go way back into the 1600s, there was what's known as the Maunder minimum. It was a fairly long period, 1645 to 1715, I believe, somewhere in that range, last half of the 17th century, and there's basically no sunspots. There's a 28-year period where there were 50 recorded sunspots. We have well over 100 on the sun right now. So that was particularly unusual. Hopefully that doesn't happen again. So you can see that there's that really repetitive cycle, and each one of those is a flip in the sun's polarization. So a pair of them is supposed to be a full solar cycle. But that doesn't tell us anything about the aurora. So if we go look at aurora stats and averages see the aurora. I cut it there because I had an annoying ad pop up. So let's expand this. So we can see the full solar cycle going back in time. Also on here is the geomagnetic storms KP5 plus by year. So this is the number of days in that year when there was a KP5 geomagnetic storm. Now that might not happen at night, but that's still a lot of days. 175 is half the days of the year approximately had a geomagnetic storm in 2003. That'd be a good year for hunting aurora. You can see in the last cycle it didn't get over 70 days with KP5. So if we expand this, 175 looked really high, but in comparison to other peaks it's not unusual. So it's not unusual for the years with peak aurora activity to be every second day there's a geomagnetic storm. They probably would occur in clusters, because there'd be an active region that is generating that activity that's driving it. So it becomes more interesting when we scroll down here and overlay those two graphs together. So the yellow is the sunspot numbers for the last two cycles, and you can see the number of days with KP5 plus geomagnetic storms sort of very approximately follows the sunspots. And if I expand it by pushing the right button, I think there's a pretty definite pattern that the peak often occurs after the sunspot peak. A year or two after. The peak's there, the peak's there. There is a definite pattern. Remember the latest dates are on the left here. But there's a definite pattern there where the sunspot peak is or the sunspots peak, and then sometime later, a year or two later, we get the geomagnetic storm peak. And I don't know for certain the answer to that, but I suspect I know what it is. At the sunspot peak, the sunspots are about 30 degrees, on average about 30 degrees north of the equators. And then after the peak, they start moving closer to the equators. And if CME erupts from near the equator, they are more likely to hit and interact with the Earth, because the Earth is on the equatorial plane. So the same with coronal holes. If they are sitting over the equator, they're more likely to interact with the Earth, just because they are sending out along the plane with like planets on it, including Earth, of course. So I think there's the two takeaways: that there's definitely quite a bit of variation on the number of high KP days when there's more sunspots, but it actually seems to happen a little bit later in the cycle after the sunspot peak. And then the other is that it doesn't go to zero. So other than here, where this year here, where we basically had no sunspots and no KP5 days, the minimum, this minimum isn't that much lower than the peak that we had in 2015, and sometimes possibly even higher. So it's not like the Aurora completely goes away. We still have geomagnetic storms, although also, as you can see, there's quite a bit of variation in there. So once we pass the peak, certainly don't give up on Aurora hunting, because there's certainly many good years following, and then there is continued activity most years. The solar cycle is the 22-year period in which the sun's magnetic field flips twice, first one way and then back to the original. During each flip, the number of sunspots increases and then decreases. This is the 11-year sunspot cycle, which is confusingly often called the solar cycle. More sunspots and the associated CMEs generally result in more geomagnetic activity on the Earth, as well as more auroral activity. Historically, the peak in geomagnetic activity peaks after the sunspot numbers peak. This may be due to the migration of the sunspots towards the equator, placing them in an ideal location to impact the Earth. With that, please check out episode 16, How Do I Use SpaceWeatherLive.com, and I'm wishing you clear skies and happy hunting.